Look at this abstract 3D space. These white arrows, vectors A and B, are defined by magnitude and direction. Applying scalar multiplication by a numerical value, lambda, only scales magnitude. If lambda is 2, the vector doubles in length. If negative, it reverses direction entirely. But scaling or adding vectors element-wise leaves a critical gap in our toolset. These basic operations cannot calculate how two distinct forces physically interact with one another when they meet in shared space. Consider the physical forces acting on this aircraft wing. To model the aerodynamic torque snapping that aileron upward, to calculate electromagnetic deflection in a particle accelerator, or to render real-time lighting on a digital surface, we need these intersecting forces to interact. To mathematically simulate these systems, we must transition from merely scaling single vectors to multiplying them together. When we multiply vectors, the mathematics divides into two distinct behaviors. The first behavior is the dot product. This operation is a tool for measuring parallel alignment, quantifying exactly how much two vectors are pulling in the same direction. The second behavior is the cross product. This operation does the inverse, measuring orthogonal generation, determining how two intersecting vectors spawn an entirely new perpendicular force. This divide between parallel measurement and orthogonal generation forms the structural bedrock for modern aerospace engineering, modern circuit design, and computer science. By breaking down these two mathematical operations side by side, we can map exactly how they divide the computational labor of physics. This diagram illustrates the mechanics of the dot product. Algebraically, vector A dot vector B equals the magnitude of A times the magnitude of B multiplied by the cosine of theta. Notice the dashed line dropping perpendicularly from B onto A, isolating a glowing orange segment representing parallel projection. It's like vector B casting a mathematical shadow. As the angle shifts, the shadow grows and shrinks. The output of this calculation is a scalar, a single numerical value. It does not create a new spatial vector. It simply outputs a magnitude representing the degree of overlap. Governed by the cosine of theta, perfectly aligned vectors yield a maximum dot product. But when vector B locks into a 90-degree angle with A, the orange projection vanishes. The cosine of 90 degrees is 0, so the output falls to 0. This provides the mathematical basis for an orthogonality check. If the dot product of two non-zero vectors equals 0, those vectors are perpendicular. The dot product acts as a mathematical filter, stripping away perpendicular noise to measure precisely how much two forces are working together along the same path. We see this applied in aerospace engineering. This diagram charts an orange thrust vector projecting onto an intersecting wind current vector, creating an isolated segment labeled effective velocity. When navigating dynamic wind currents, an aircraft's engines point one way, while the atmosphere pushes another. Engineers calculate the dot product to strip away lateral wind drag, isolating the component of engine thrust that translates to true forward velocity. The same logic applies to electronics when calculating real power in alternating current circuits. Real power relies on determining the alignment between voltage and current phasors. By taking the cosine of the phase angle difference between them, electrical engineers run the same dot product calculation used to track an aircraft's thrust. In computer graphics, the dot product governs diffuse lighting. On screen is a 3D polygon surface with a normal vector pointing straight outward, interacting with an incoming light ray vector. To calculate pixel brightness, rendering engines compute the dot product between the 3D surface's normal vector and the light source. The mathematical output controls the visual brightness. A dot product of 1 means the light vector is hitting the surface straight on, yielding maximum brightness. An output of 0 or less means the light is striking at a perpendicular or negative angle, causing the surface to be rendered in shadow. Whether isolating aerodynamic momentum, electrical output, or digital brightness, whenever an engineer needs to measure alignment, they use the dot product. Now we transition to the cross product. Here we have vectors A and B resting flat on a 2D plane, bounded by a blue spatial parallelogram. Algebraically, it equals the magnitude of A times B times the sine of theta multiplied by n hat. As the operation completes, this new unit vector n hat emerges perpendicular to the flat 2D plane. The magnitude of this newly generated vector is equivalent to the geometric area of the spatial parallelogram formed by A and B. This operation is driven by the sine of theta. Because the sine function reaches its maximum at 90 degrees, the cross product generates its longest vector when the original forces are perpendicular. To map this new dimension, physicists use the right-hand rule. Align your indexed and middle fingers with vectors A and B. Your thumb reveals the resulting trajectory. If the vectors point in the same direction, the sine of 0 is 0, and the cross product yields an empty 0 vector. Where the dot product measured overlap, the cross product utilizes flat intersecting lines to construct independent spatial dimensions. Returning to aerospace, we can map this behavior to physical rotation. This diagram shows an aileron hinge point, displaying a radial distance vector intersecting with an applied aerodynamic force. The aerodynamic torque, the force required to move that control surface, is the cross product of the radial distance and the applied air pressure. This calculation produces the perpendicular axis of rotation that rolls the aircraft. In electromagnetism, the cross product defines the Lorentz force. A charged particle speeds down an accelerator tube, violently deflecting as it hits a magnetic field. That sharp deflection is the Lorentz mechanism. When a moving charge's velocity vector crosses with a magnetic field vector, the resulting force is thrust outward, orthogonal to both. In computing, 3D physics engines run continuous cross products to process collision detection. Look at this complex 3D wireframe mesh. Every polygon surface must generate a perpendicular normal vector to define its boundaries, represented here by the blue lines sprouting from the center of each individual triangle. Game engines generate these normals by running a cross-product calculation on the edges of every triangle in a mesh. Those normal vectors dictate how a digital object bounces off a wall or deflects a projectile. Whether an airplane rolls, a particle deflects, or a digital character hits a solid wall, the cross product executes the physics. In modern engineering, developers translate vector geometry into executable Python arrays. As shown here, they use computational libraries to handle these operations at scale. Developers call functions like numpy ... to scan arrays of directional data, filtering thousands of forces for perfect orthogonality in milliseconds. In the same script, numpy.cross is deployed to compute spatial area and mass generate the perpendicular surface normals required for 3D physics meshes. By stripping down complex geometric rules into programmable arrays, engineers secure the processing bandwidth necessary to simulate physical environments in real time. The mathematical foundation of 3D vector interaction is built on this specific duality, isolating alignment via cosine versus generating perpendicular forces via sine. The math remains consistent regardless of scale. The same trigonometric rules that isolate the torque on a mechanical hinge are utilized to calculate the diffuse light bouncing off millions of polygons in a digital landscape. Vector multiplication provides the structural logic for simulation, electrical grids, and flight systems currently in operation. Observe the specific mechanics of these forces, either aligning to build forward momentum or crossing to generate rotation. Mastering these products provides the framework to translate raw magnitudes into the calculated thrust, lighting, and torque that define modern engineering.